fate?
Sì, il punto è che mi chiedono di trasmettere su YouTube, sul canale del Dipartimento, che è una rottura di scatole, però lo facciamo più volentieri. Adesso magicamente è apparso il quesito. Ma qual è la rotazione giusta?
Scusa, questo è il computer, il microfono è questo qua?
Il microfono tu stai vicino, tu stai da queste parti qua davanti, il microfono
io sto davanti?
Poi stai davanti, usi questo per scorrere e qui, scusami, e qui lui ti prende col microfono.
Prova a cambiare un attimo quello che c'è, che vedo quale vedo dirette cambia.
Sai che abbiamo 30 secondi, tanto sposto le mie cose.
Ah guarda, una delle due si è conclusa.
Forse questa luce la spegno. Sì, adesso proviamo a farlo. Aspetta.
Una delle due è finita, penso che sia l'altra quella giusta.
Non so se mi sentono.
No, è vero perché è una grande casina.
Perché non si può fare non si può usare questo?
No, sarà che vediamo.
Poi c'è questo scambio. No, questo non fa parte che non è
Però se parli minimamente, lui non ti amplifica, ma se parli minimamente ad alta voce ce lo dovremo fare.
Ok.
Secondo me non c'è problema. Fammi solo fare questa cosa qua. Ti lancio.
Puoi anche non lanciarlo. Mi lancio da solo.
Giacomo, tutto ok? Okay, hi guys, thank you to be here. This is the fourth, if I remember correctly, AI seminar. I am very happy to have here Riccardo Zecchina. Riccardo Zecchina, he is the head of the Department of Computing Sciences at Bocconi University. Riccardo is working, is working from a lot of time in physics and specifically in complex systems. Tell me whether I am wrong. He is a ERC laureate and, again, he is currently the guy that is working at Bocconi in order to to guide the AI department.
Thank you very much, Nicola. So, yeah, I was an engineer by training, and then I did PhD in theoretical physics, but I've always been learning in computation, using tools coming from physics. That's a minor aspect. Okay, so very happy to be here to see a lot of young people. So today we'd like to do a couple of things. One is to review some of the work that all these people doing on the learning landscape of deep networks, or say non-convex neural networks, which I think we all agree is a challenge. And then I'd like to discuss with you some very recent results about which I'm very, excited. Not published yet, but I think it's nice to show also, without any fear what's going on, at the risk of being wrong. Anyhow, so first of all, I will not go into technicalities unless you ask, which is totally fine. You can also just reach 1/4 of the seminar, and if you want to know something about the analytical tools that we are using, that's totally fine. So the kind of tools we are using have been developed in the 80s to study, say, the behavior of physical systems that are described by an energy function that has this form here, which means essentially that depending on the variables the configuration of the variable, the energy landscape is highly non-convex. And these, the tools that have been invented to study these problems have led to the Nobel Prize in Geophysics a couple of years ago. Okay, so that to say it's a non-trivial tour de force. And these kind of tools have been used, say, in the 80s to study the capacity of very simple devices like the Hoffman model, which is an attractor network with an associative memory. And by using this kind of technique, you can show that you can actually store a number of random patterns in an attractor network, which is 0.14 times the size of the network, n. Okay? And so this result was derived in '85 using the replica method developed by Parisi. And then it has been used, say, in machine learning to study the capacity of feed-forward networks with at most one hidden layer, not more, because then it becomes just too involved, but still, that's an old story. Okay? And just to give you some reference name, the analytical tools are called replica method or cavity method. They kind of are equivalent. And the analytical tools allow you to estimate the most probable behavior of a random system, so a system characterized by a large set of random parameters, and you can still estimate, under certain assumptions, which is the most probable behavior. So, for instance, in the case of the Hoffman model, you can show that the probability tending to 1 as the system becomes large, you can store a number of patterns, which is 0.14 the size of the system. Okay, so it's a probabilistic tool. And it also has an algorithmic counterpart, so you can actually derive algorithms from this tool, and these algorithms are very well known by engineers in the area of communication. So, for instance, belief propagation, it's just a version of the so-called cavity method developed in this field, but there are also more sophisticated techniques like circuit propagation, which deal with problems that are highly non-convex that can be used for optimization. Okay, so this is just an historical excursus, and all these the tools have been used in to study learning problems, constraint satisfaction problems, codes, error correcting codes. Many of the works of, for instance, Andrea Montanari that have been built on these kind of tools, and they've been applied to many fields. For instance, in the case of the prediction of protein contacts, these techniques have been very successful, and actually the pre-processing which is present in AlphaFold has to do with this. That's okay. I want to give you an example of how powerful this technique by not talking about machine learning. Then I will go to machine learning, okay, to AI. But let's take something that we all know, which is the satisfiability problem. We know that this is the mother of all incomplete problems, right? And then let's say that we take a random a K-sat problem and we draw clauses at random. So we build a formula which is built, say, of clauses made of K literals, let's say K equals 3, well, K equals 2 is polynomial, right? So K equals 3. And let's say we create a random formula like this. And so we just build a formula composed of M clauses and N variables, which can be negated inside the clauses with probability 1/2, okay? And you draw this formula at random, and you would like to know, well, what's going to happen in this formula, okay? And okay, so it turns out that you can think of this formula as a factor graph, like in error correcting code. So you associate to each clause a factor node, and this factor node has a cost equal to 1 if the clause is violated and 0 if the clause is satisfied. So essentially what you want to do is to find a configuration of the binary variables such that the sum of the cost of all these nodes is equal to 0, which means that all clauses are satisfied simultaneously. So you see, you can think of this as a kind of an energy function for which you want to find a minimum, okay? Which should be 0, which is bounded below by 0. And if you build this formula, it's pretty interesting because you can show that there is a critical, for instance, the case K equals 3, there is a critical ratio of the number of clauses to the number of variables in the limit in which both go to infinity, at which, with probability 1, the formula becomes unsatisfiable. Okay? This is the so-called SAT and SAT transition. It has been studied a lot, say, kind of 10, 15 years ago. And So it's pretty interesting because by using the techniques based on the replica method, you can actually predict which is this value of the threshold. It's actually the only tool that can give you this. It has been proven to be correct, say, 15 years after the result was actually obtained, was proved in the sense by other techniques. And this is fine, but what is even more interesting is that, you see, at this point here, so when you have about a number of clauses which is about 4 times the number of variables, all of a sudden the formula becomes unsatisfiable. But what is interesting is that just before this threshold, all the known algorithms start to diverge exponentially. So they cannot find solution efficiently. So you have a satisfiability problem, you want to find an assignment of the binary variable such that all the clauses are satisfied, and just before this threshold, all the algorithms fail. So what's going on there? It's kind of, this is where the hard instances happen. Well, by using this techniques based on the replica and the cavity method, you can actually show that just before there is a region before this SAT and SAT transition where the space of solution, so the space of satisfying assignment, all of a sudden breaks into an exponential number of little clusters of solutions which are far apart in Hamming distance. It's called the shattering transition. Okay? And by using these analytical tools, you can actually predict which are the marginals of the variables within each cluster, and also how this marginal change from cluster to cluster. So you have a probability distribution over a space of functions. Okay, it's a pretty sophisticated thing from which you can also derive algorithms. And so essentially for this kind of problem, you can show that as you increase the ratio of constraints over the ratio of the number of variables, you start with a very easy problem. If there are no clauses, all the configurations are satisfying assignment, let's say. And then as you increase the number of constraints, the space of solutions of satisfying assignment starts to break into many clusters, but you have a dominant one, which is easy to find by algorithms. But then there is a region where this big cluster breaks into an exponential number of smaller clusters, and you can also show that at a finite number of violated clauses, you have a lot of local minima of the function. And this is where all the known algorithms, most of the algorithms fail. Okay? So you start to have an idea of what's happening, why the problem becomes hard. And this is very important nowadays for cryptography. In cryptography, you're interested in, say, post-quantum cryptography, you want to build systems that are hard on average with probability 1, right? Which are maybe random so that you cannot exploit symmetries of quantum computing. Okay, so this was just an historical review, just to show you kind of how powerful are these techniques. And now let's go to neural networks. I mean, in constraint satisfaction problem, you're happy if you find an assignment that satisfies all constraints, right? But in neural network, that's not really the case. You can think of that each pattern you present, each input-output relation to a deep network is a kind of constraint you're imposing on the weights of the network, right? But it's not enough that you find a configuration of the weights that classify correctly all the patterns. You also want them to generalize well. So which kind of minima do you want to find actually? So it's not, it's not the same thing finding a solution, let's say here or here. They have different properties. So we need to know how the landscape looks like and try to understand what the algorithms are actually doing. Given that the problem is non-convex, so most likely it's going to present something like this. There's a scenario. Okay? So this is the kind of, so just to say that all this is a very nice story, so random systems, hard combinatorial problems, so however, why didn't we, I mean, theoreticians, and not only us that using these techniques, also the other theoreticians, why didn't we predict, say, the deep learning revolution? Why did are we following practitioners in a sense? Why didn't we anticipate what was happening? Okay? Maybe it's true, yes, the data, the computer power, blah, 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 but maybe we were also missing something from a theoretical point of view. And this is what I'm going to talk about today, at least in my perspective. So this is, say, okay, so the kind of tools that I've discussed with you have been used in the context of neural networks a lot in the 90s, and then there was a kind of a winter, and you know that there was a winter of AI, and in this period, my community started to study hard combinatorial problems, and so we created a very strong link with computer science. Actually, now there is a field of probability and computer science that deals with this kind of, because just let me open a parenthesis. It's clear that essentially these are the tools that are needed to understand non-convex problems. Otherwise, you're confined to convex problems. So I'm a bit exaggerating here, but really it is a tool for analyzing non-convex problems. And okay, so there was something missing. Okay, so let's try to understand what was missing. So I guess we agree that training a large-scale deep network is, in principle, a hard computational problem because it's a non-convex problem, and yet what we observe is that algorithms are relatively efficient in solving these problems. Even algorithms that have been designed for convex problems, that's the disturbing part of it, they can find solutions that have very good generalization properties, and they don't suffer of overfitting, or at least it can be kept under control. I mean, for all of us who have been studying, say, machine learning in the 90s, this is kind of a dream, right? For you, no, because you're born already with this, with this reality around you. But for those of us who are older, this has been a big jump. Okay, let's try to understand what happens. Let's apply these tools. So let's consider, okay, a typical setting of a feed-forward neural network. So we have an input, we have an output, we have a training set, and then the output is just the composition of all the layers. So it's a highly nonlinear function. Okay, where sigma is the nonlinearity applied elementalized. I guess we all I'm trying to go fast because I guess we're all familiar with neural networks so this is the kind of setup we are going to consider, and then okay, the kind of loss function that I'm going to consider here is the 0-1 loss function. So I call it number of errors. Okay, because this is actually, in principle, is the true loss function. So you are given, in principle, you are given some examples. You can measure the training set errors, and then you want to estimate the generalization error. All the other loss functions are surrogate loss functions that are created in order to use gradients. Okay, but this is, let me say, the true reality behind all this. And then you have, typically the mean square error or the cross entropy or other variants, plus regularization tools. Okay, we all agree on this, right? So what we're going to do now is just to study problems with this kind of loss function and try to analyze how does the landscape look like in terms of number of errors as you change the variables, the W's for a given training set. Okay, everything in the limit of large system sizes. Is that clear? Okay, and so how are we going to study this? Well, we're going to study this by trying to compute what is called the Gibbs measure. So imagine that you are able to compute this probability distribution over the weights. Assume that the training set is a random patterns, and you construct this probability measure. Z is called partition function, is the normalization factor, and you have e to the minus beta, the cost function. Clearly, if this parameter beta is equal to 0, this probability distribution is just flat. Just all configurations are weighted equally. It doesn't see anything, right? But if you take this beta going to infinity, then this probability measure is going to concentrate on the minima of the cost function. So if you are able to compute this quantity and take the limit beta going to infinity, we are going to have in our hands a probability distribution that is going to concentrate on the minima of the loss function and tell us how this minima look like. Okay? This is where the connection with, so this is called the Boltzmann-Gibbs measure, and has been used in theoretical physics to study, say, complex systems, exactly, but it's just a mathematical tool. You can think of this as just the generating function of cost levels. It's just the same thing, so in mathematical terms. Okay? So, so the idea is that we compute this, and then by changing this beta, we are going to see how the landscape changes. Okay? So in particular, the kind of issue we are going to analyze is the following: is that in general, let's assume that this loss function is highly non-convex. So you can imagine that the loss function is something like this, a very rugged landscape, and it has certain minima, say, of 0 error, in which the training set is totally correctly classified, so number of errors equal to 0, and it has a lot of minima. Now, this probability distribution here is dominated, we say it's dominated by these green points. Why? Because they are the most numerous ones. So this probability distribution is dominated by this narrow minima in this picture, this narrow minima which give the greatest contribution to this probability measure because they have zero energy and there are a lot of them. But maybe in the landscape you might have also minima like this that are very rare, okay, that are very rare, but still have a zero energy, which correspond to so-called subdominant contribution in probabilistic terms. So you can only access them by looking at large deviations. But okay, let's just to say that this might be rare, but it could be that the algorithm actually focus exactly on this minimum. We don't know this a priori. We have to check it out. Okay. So the kind of question. So okay, let me make a long story short. In the 90s, we were all focused on studying this dominating minima. So we were studying the most probable minima of this function. But these minima are actually not accessible by algorithm. They get stuck in the local, the kind of minima of algorithms that try to find this minima get stuck in the local minima around it. Whereas algorithms that are created to target large, rare minima, they actually do not suffer by trapping of these local minima and can actually converge in this wide minima. The problem is that these wide minima are rare, and so you have to look for them in the probability measure. They are hidden in the tail of the probability measure, and we didn't do this in the 90s. Okay? This is what the conceptual challenge it was missing. My opinion, I was there. So, but unfortunately, and okay, is that the scenario? Is that clear? So the question is this true? Is this really happening in deep networks? Okay, say non-convex networks. Okay, so let's study this. Okay, I think I've already explained to you this. And so the kind of problems that we have been studying already some years ago are the minimal models which display non-convexity. Okay, of course we are not able to study 150 layers of a convolutional network just because analytically you cannot even write it down. Okay, it's very complicated. But already this kind of network, so just with one hidden layer, is actually pretty complex to analyze. And so what we're doing is we are studying this kind of architecture, storing random patterns. And by changing the number of patterns which are memorized by this network, we can analyze the structure of the space, including rare minima, which might be accessible. And okay, this is, and also if we generate a pattern with another network, we can also compute the generalization capability of this network with the teacher-student scenario. So we can check whether this network is capable of inferring a rule where this rule is generated by a similar network that has generated the pattern that are given for training. Is that clear, or is that clear? I don't want to take a tangent and then be left alone. If there's something you want to discuss, please. I mean, so I really appreciate the spirit and the engineering spirit, and you will see that the aim here was to build algorithms at the end, not just to do some nice theory. Okay. So, any question in this sense? So, okay. Just to don't read. Let's focus just on this picture. So, if you apply the tools to this kind of networks, what you find, and we are here is in the case of binary weights, but it's just for simplicity, is the following scenario: is that as you start to learn an extensive number of patterns, or of the order of the number of weights that you have isolated solutions. So that all the minima are like the narrow minima that I've shown to you before. You can actually compute this. You can compute the radius of this minima, how many minima are around the given minima, okay? And they're very, very tiny. So the radius is almost square root of n. So divided by n, it's actually a point. And so this is the scenario. You have a lot of solution, an exponential number of solutions, however, they are all narrow. And as you increase the number of patterns, this number of solutions start to disappear. At a certain point, you reach the capacity of the network. Okay? Is that clear? Now, if you are in a situation like this, this is nothing but a golf course. So you have a very rugged landscape with some holes here and there which are far apart. there's no hope you can actually find the solution. If you could find the solution, you would build a fantastic cryptographic system. So believe me, there's no way you can find this solution. So it's a bit disturbing. These very simple networks, which are non-convex, are actually apparently not trainable. In fact, this is not the case. If you start to play with some heuristics, you do find solution. So there's something contradiction here. Theory predicts no way, practice says yes. So what we did is say, okay, maybe there are rare solutions which are not captured by just computing the most numerous type of minima, which play a role here. Okay, is that clear? So what we did is to, there's a technique which allows you to compute the distance between these minima, and this distance is always of order n in Hamming distance. So all these points differ by an order n number of big trees. And if you run, for instance, a simulated annealing or your favorite optimization algorithm, you see that you get stuck. And as the size of the system increases, you will never be able to find a solution. Okay, so what we did is to look for minima of this type in this kind of landscape. Okay? So let me jump to how we did this. So instead of, we designed a new tool, which is called the local entropy measure, which is the following. Instead of looking for solution, we ask the following geometrical question. Let me define on the hypercube, say, a ball of radius d, a hypersphere of radius d, and I ask myself, I move around this hypersphere, and I ask myself, does it exist this hypersphere of radius d that contains an exponential number of solutions, where d is something that I can change? So you agree with me that if the situation is this one, at a certain point, by changing the radius of this hypersphere, you will reach a situation in which you have just one solution inside, and therefore the answer would be, well, the log of this number will be 0. Okay? Whereas we're looking for regions in which you have a dense population of solutions. So we are looking for something which is exponential. So this is why we take the log. So with this in mind, what we define is a new energy function, which is minus the log of the number of solutions around a vector W of weights within a distance d. Is that clear? So by trying to minimize this, there is a minus sign here, so you're looking for spheres of extensive radius that contain an enormous number of solutions. So we know already that if you look at just to the dominant state, this calculation should give something trivial, because as you reduce d below a certain level, you would find 0. Is that you all agree? So when we started to do this was a high-risk calculation, because it takes months to do this kind of calculations. They are very complicated. Also, there was a big hope of not reaching anything. But we had some numerical evidence that this, of course, this should have been the case, but we were not sure. Okay, so we did this kind of calculation, and the idea is that this local entropy, this new energy function, is as you change the radius, it kind of, if you consider a large radius and you look at the profile of this local entropy, it's something very smooth, and then as you reduce it, it concentrates on the wider minima. And so you can actually think to create an algorithm that optimizes this function, and then as the algorithm proceeds, you reduce the radius such that you start from a convex kind of landscape, and then you make it more and more non-convex. Okay? And okay, we did all the calculation. I skip all the details, and what we found that in fact, in this non-convex network, there exist regions that are extremely dense in solution. This was really a discovery in 2015. I'm not saying it's a big discovery, but we'll see. So, and you can see here that here is the log of the number, and here is the distance. So it's very small, but you can you see these curves here show that there exist solutions that have a very high entropy. The entropy is 1 over n the log of the number. So they have an exponential number of solutions within a certain radius. Whereas if you look at the typical solution, this point-like solution, you see that below a certain distance, their entropy goes to 0. So normally there is a gap below which the hypersphere is empty, this little ball is empty, but whereas if you try to optimize the positions, there exist regions that, and so this was the first thing, and one can also be a little bit more sophisticated and show that these dense regions are contained inside high margin configurations. One can show this analytically. So those solutions, those configurations of weights which satisfy the training set with margin typically belong to this dense region, are closer by. This is, it should ring a bell because this is going to tell us that this solution will generalize well. Okay? And so more or less this was the outcome of the calculation. So you have to imagine that you have a population of solution which is dominated by isolated solution, but then there are these clusters that are very rare but extremely dense. And this was proven by other techniques in 2021 by Alan Sly and other guys. And you see these two pictures are very funny because this is the picture we made, and this is the very same picture made by some mathematician. Clearly, we have different kind of perception. Are both wrong because this is a high dimensional object. So, but the idea is that you have all these solutions and then you have some structured solutions which are interesting because they're extremely dense. Now, by rewriting things, and I don't have really time, I don't want to bother you too much, but you can rewrite things in a proper way such that you can actually turn this large deviation technique into an algorithm. And the algorithm, let me see, okay, and the algorithm does simply the following. Suppose you have a certain cost function, then you take y, a number of replicas of this cost function, and then you impose a distance constraint between this replicated system. Okay? So imagine you have a centroid plus replicas kept at a certain distance d. If you try to optimize this system, instead of having say, just one neural network, you have 10 neural networks that are forced to be at a certain distance apart, and you try to optimize this, the global system, the sum of all these systems which are constraints among themselves, you can show that analytically this corresponds to finding the rare regions in the landscape. So immediately you have an algorithm which you can test, and it works. Okay? So this is the engineering part. So you take all these tools, and so these are all kind of algorithms which can be derived from this kind of approach. So you can do simulated annealing on this replicated system, and it works beautifully. Or you can do message passing, belief propagation on this replicated system, and again it works. You have replicated stochastic gradient, entropy SGD, which is probably the most famous one in the context of machine learning, but it's just a stochastic gradient in which between each update you have an internal loop that tries to estimate the density of solution around a given solution. And then there's this sharpness aware minimization, which is again another very efficient algorithm to target flat regions and so on and so forth. Okay? So these are some of the algorithms. Essentially, this algorithm disregard the narrow minima and go to the wide minima. Is that clear? Now, this is all what I've said, even though here it's applied to deep networks. The kind of analysis we have done is not for over-parameterized networks, just for neural networks in which the number of parameters is of the order of the number of patterns. Okay? Now, the kind of algorithm that has been developed can be applied to over-parameterized system, but we didn't analyze over-parameterized system. So what we did more recently is to analyze over-parameterized system and see what happens. Because I bet the following. If I ask you, suppose you have a deep network in which you have a huge number of parameters, okay, and you're given training set. As you increase the size of the network, you expect your problem to become convex. I asked Marcello once. Okay, do you expect the problem to become convex? Effectively convex. Try to answer this question. I bet, because this is also mine, but I bet that what your idea would be the following. Well, maybe it's not convex, but the majority of the volume will be associated to some few minima. So it's effectively convex, right? This would be the guess. And I'm going to show you that this is not the case. So this is you have to live with it. I mean, we are going to show this in a given non-convex model. So whether this is fully general, it's an open discussion. But so the intuition is, to explain why algorithm works in this complicated network, one can train well, it's because it becomes effectively complex. No, that's not the case. Okay? So, and also we'd like to understand this idea of benign overfitting, which is also another challenge. Okay? So, we all agree that, well, one of the most probably beautiful results in deep learning from a theoretical point of view is this idea that you do not have this overfitting catastrophe. Okay? So this idea that you can train a huge model and they still generalize well because you're able to regularize somehow, this is really a beautiful result, which hopefully is going to, and actually this is was one of the first systematic studies on the effect of the size on the network, and this is the generalization error, and here, and this is the size of the network on, I don't remember which kind of data set, probably cipher. No, this is for probably at least, and you see that there's no overfitting. Okay, you increase the size. So this is a simulation done by these guys here, in which they let the system converge, and they estimate the generalization error. They increase the size, they converge, and so on and so forth. So here is the size, and here is the final generalization error. You see that as you increase the size, the generalization just goes smoothly. It does not present this U-shaped trade-off between bias and variance, which we all know. Okay? So, and also we know that this network are also capable of memorizing random labels, randomized labels. So again, this is something that contradicts our intuition from classical statistical inference. Okay? So there is a model that allows you to study the effect of overparameterization, which is called the random feature model. Essentially what you do is that you generate these are your input, say, patterns, you project them randomly into high-dimensional space, and then you classify them somehow. So normally this model, which was introduced by these guys, is analyzed by putting here a convex device, like just a linear classifier, okay? And if you analyze this model, you actually find that it's true that the error increases as you reach, as the complexity increases, but then you have a double descent. So beyond a certain threshold, the error generalization goes down again, which means that if you increase the size of this hidden layer, at the beginning you have overfitting, but then this disappears. So in the limit of wide network, they generalize well. Okay, this is a beautiful result. And of course, if you actually regularize your system, you're not even going to see this peak, by the way. So you just see the error that goes down like this. But this is something that you can handle. So what we did is to study, okay, these are all the work that have been done, if you want, some of the work that has been done on linear classifiers and so-called double descent problem. And there have been some experiments showing that this happens also in non-convex devices in deep networks by these guys here. So somehow this kind of double descent curve. And so how did we approach this? Well, we said, okay, let's take some random projection here. You start with the input dimension D, you project in a higher, in n dimension, from D you go to n dimension. D and n are proportional, but typically n is much bigger than D. And then we put here, instead of a linear classifier, a non-linear classifier, a non-convex classifier. Okay? And so we can actually control the degree of overparameterization, and we can at the same time have a non-convex classifier following the. And so this is what we did, and okay, let me go directly to the results. With what we have shown is that as you increase, you have to follow this vertical line. As you increase the size of your system, so the projection, you are moving downward in this plot. There's some definition that I don't really want to bother you with this definition, but just intuitively what you get is that as you move along this line, you increase the size of your system, you first hit. So imagine that you start with a very small system. You are not able to fit the data. You increase the size. At a certain point, you hit a point where you can show analytically that solution starts to exist. This is an analytical calculation. It does not, on average, over random patterns and so on. So we don't need an algorithm to actually check this. It's just an analytical calculation. We show that solution exists even though we are not able to find it. Okay? So at a certain point, you hit a line beyond which solutions start, so you increase the size, solutions start to appear, and they look like this. They are kind of point-like solution. And then there is a second transition where wide minima start to appear. And then you can show that algorithms actually stop exactly where the wide minima start to appear. So, or they say start to function where the wide minima start to appear. Okay? And so I think this is a result that shows that when you have this overparameterized system, you actually have two thresholds. One is the information theoretics threshold, which is the threshold at which solutions start to appear, and then is an algorithmic threshold where the solution becomes accessible by algorithms. So, and this is to answer the question that I posted before. One can show that the number of narrow minima is always much bigger than the number of this. The number of solutions which are narrow is much bigger than the number of solutions contained in wide minima. So the problem does not become convex at all, and the volume associated to narrow solution is always bigger. But the point is that algorithms are actually effective in finding this wide minima. Stochastic gradient, we know very well that has this self-regularization property, okay, and initial conditions are crucial. So the fact that stochastic gradient keeps the norm under control leads to this kind of minima. Or you can have other type of algorithm, all the kind of dropout, all this kind of technique actually are techniques such that you end up in this kind of larger minima. If you think about it, the only algorithm that would want to minimize the number of errors would be the full gradient, and you never use that. All the other algorithms do not optimize the loss function, they do something else. They optimize the loss function plus some noise, plus some regularizations, and so somehow they choose which kind of minima they are going to target in the loss landscape. Okay? So I will try to. Okay, so there's been a lot of work on this, and in order to analyze what happens in this deep network, you have to be careful because deep network have a lot of symmetries, and so in order to analyze the minima numerically of deep networks, you have first to remove all the symmetries from your network, and then in the space of the function implemented, not in the compare networks. And if you do this, you can actually show that depending on initial condition, depending on the kind of algorithm, you target different type of minima. Okay? So our paper was titled Deep Networks on Toroids. Sorry, very terrible name. But what this means is that we are going to consider deep network in which we fix the norm of the weights, we get rid of all the symmetries, and then when we compare networks, we actually do a maximum matching operation before comparing the network across permutation of the hidden nodes, and also a scaling of the ReLU transfer function. Okay, so this is, there's been a lot of experiments. There was this very expensive experiment by the Google group in which they studied more than 10,000 models looking at 40 different predictors of generalization errors, and they essentially what they concluded that sharpness-based complexity measures are those that best correlate with generalization, and we can actually compute this for given, as I told you, in a teacher-student scenario where we know what we can compute the generalization error that wide solution generalize better than narrow solution. Okay? And we are currently working on using this technique for various applications, and in particular pruning, continual learning, and all this kind of stuff. But I think it gives some idea on why non-convexity and learning are compatible. Not only. So this is the first case in which kind of two nice properties come together instead of fighting. Normally you always have to find a trade-off. In this case, you maximize flatness and maximize generalization, and also those minima are the easy one to find. Okay, so we are really lucky, in a sense. Okay, so this was a brief review of what we've been doing in our group in the last 3 or 4 years, and now I would like to tell you about something on which we've been working in the last month or so, which I think is I'm particularly excited about, but I don't know. Do you have any questions about what I've just told you? Any curiosity or?
Yeah.
Yeah.
Curiosity.
Yeah.
I'm not an expert, so
No worries.
I do apologize for the lag. So you show that when you increase the size, then you have several local minima. But I was wondering, and the number increases with the size.
Yes.
But what about the number of flat minima?
Yeah.
Do they increase, and then if the
Yes.
number increase, how to handle it?
So they do increase. You have multiple flat minima. They all generalize well. They are typically okay. You should think that these minima are not really isolated. It's like you have to imagine geometrically to have a region which is somehow dense here, and then you have some corridors that connect these regions in high dimension. That's the idea of narrow wide. So essentially, you have to imagine a landscape in which you have dense regions and then narrow minima here and there, and they might be connected, but it's a matter of modulating the density. What I wanted to say is that the total volume associated to non-dense parts of this landscape is much bigger than the volume associated to the dense parts. So they remain subdominant even when the network becomes big. So it's true that they increase, but the narrow one increases even more, exponentially more. But this is not a problem for algorithm, luckily enough. Because essentially, okay, we are engineers, you apply a low-pass filter. All the in the space, so all the fluctuation of the loss function on short distances are cut away by the algorithm, so you get in this wide minimum. That's the kind of intuition. Okay, now I want to move to the second topic, which is something I'm doing right now, really doing in these days. So I put together the slides really in the last couple of days just to share. And it is the following. Well, I'm sure you have been playing with ChatGPT and so on and so forth. So I'm sure that you have the interest in transformers and the attention mechanism is something that is very clear to you, right? Transformers have had really a huge impact on deep networks. Even AlphaFold, which is used for protein predictions, this great result, is based on transformers, so it's not limited to large language models. And so, essentially, the so-called attention mechanism is very important. The attention mechanism means that essentially you have a positional encoding of your input, and you're able, by this mechanism, to detect long-distance correlation across the input, some sequential input. Whereas previous models, they were kind of recurrent networks, so they were losing memory with time. Whereas in this case, you can keep up to a certain distance, you can keep the memory. This plays a key role in transformers. Okay? And there's been a paper which is called the Hopfield network is all you need, saying that this attention mechanism can be implemented as a Hopfield network. Okay, so it's a kind of an associative memory that has an exponential capacity. That was the claim. Okay, so let's look at it a bit more in detail. What is this modern Hopfield network? It's a network in which, say, the neurons are binary, for simplicity, and they want to store some patterns like this, which can be real or binary, doesn't matter. And then you have an energy function, which is this kind of function. It's minus the sum over all the patterns, and then you have this f of the overlap between the projection of the configuration of the neuron with respect to the pattern. Okay? Sorry, this is just a product. Okay, so there is a sum missing here. Okay, sorry for that. And so this function is this nonlinear function. Okay, and you can even take, say, an exponential form, or I-degree polynomial or an exponential, and you can show that if you take an evolution dynamics of this network, in which you just flip one of the variables. Sorry, here there's a sum over I missing. I'm very sorry for this. One can show that there exists a dynamics, just like in the Hopfield network, such that this function E is a Lyapunov function of the dynamics, which means that it's bounded below and the dynamics converges to the minima, and the minima are the patterns. Okay? So this is a kind of network that is capable of storing through this kind of dynamics an enormous number of patterns, which means that if you start from one of the patterns and you put some perturbation in it, it's going to correct the errors and converge. And one can show that the attention mechanism can be implemented by this kind of system, in which you update the dynamics just one time step. So we were kind of intrigued by, what we are used to is the Hoffman model, in which n is equal to 2, which can only store 0.14 n patterns, not an exponential number of patterns. So how is it that we go from a linear number of patterns in the number of neurons to an exponential number of patterns? That's really fascinating, okay? So we started to look back, but there's a problem here, there's a catch. The catch is that if you look at this function here, you see that this function depends on the patterns. So it depends on the number of parameters, which is of the order of the number of data points. So it doesn't really mean much. It's really, if you think about it a little bit, it's a bit depressing, because this is a function that depends on an exponential number of parameters. It's really fake in a sense. Because even if you get, even if you just take n equal 3 here, which would give a quadratic capacity, what you see is that you start to have, and if you write down the function explicitly, you start to have a polynomial of third degree, which means that you have variables that interact in triples. And if you have degree 4, you have quadruples and so on. So, which means that in practice, this cannot be implemented by any means in hardware, not to mention in biology. Okay? Because in the Hoffman model, in this case here, all the information about the patterns in the couplings, the patterns are not explicitly parameterized in the function. Okay, they are summarized in the pattern. You don't want the function that depends on the patterns, otherwise it's kind of like a lookup table, right? So, and so there is a problem here. So the author of this model tried to find a way of implementing this kind of model through some meaningful interaction, but what they found is that you need a number of hidden neurons, which is of the order of number of patterns. So again, it's just, you'll go back to linear. You go back to linear because at the end, if you want an exponential number of patterns, you need an exponential number of neurons. Okay? So it took me a while to understand this. So if you have not studied it, don't just believe me, that's the case. So is there no hope of having an associative memory that somehow goes beyond the Hopfield? This is the question. This is very relevant for the interaction between machine learning and computational biology, right? It's a real key point, which I find very, very important. Well, we know, and here I'm sure some of you know better than me, that there exist systems that behave like associative memory, and these are error-correcting codes. An error-correcting code, what it does, I don't know if it's here, yes, it's here. You take a message, you encode it in a code word, then this code word goes through a channel which has some noise, and so it goes out corrupted, you correct the error, you invert the encoding, and you find back the message, right? And so you can think of this, there's all the theory of error-correcting codes that essentially it's like in a high-dimensional space, you have code word which corresponds to points, and if your message is kind of within a certain distance from your code word, you are able to recover it. So this is an associative memory. How many code words do you have? An exponential number. What is the catch? The catch is that these code words satisfy a set of constraints. So they belong to a subspace. They are correlated. They are not in generic positions. Okay? So, so you can implement this kind of exponential capacity system provided you choose your code word satisfying a set of equations. For instance, low density parity check codes, and if you're familiar with that, they just all these code words have to satisfy parity checks, which are just a set of linear equation modulo 2. So which means that, and this is the kind of constraint that both the sender and the receiver know, right? And so the code is implemented like this. So somehow, the idea is that you can have an exponential number of associative in which sense? Under the decoding dynamics, okay? You start with the corrupted code word, you decode it with some decoding dynamics, which are typically very simple, like bit propagation, or they're very simple decoding algorithms, they're very, and you decode it and you get the code word. So it's an associative memory. The problem is that you can put your code words in this position so that they satisfy a certain set of equations because you're building the code. But nature doesn't allow you to do this. You cannot choose the data at your will. So you cannot implement this directly, but at least you do have an example of a system that has this problem. And so the idea is more or less the following. Essentially, you can think that an associative memory is a kind of like an error correcting code, but where the noise is in the input and not on the channel. Because in the input you have x, and you also have x plus eta, which are other examples of inputs that belong to the same class, right? So somehow this is the idea. So essentially, independently of what's inside, we want to try to think to a system in which, say, the memories are configurations that satisfy a set of constraints. Just like in codes, code will satisfy a set of, for instance, parity check. But it has to be robust with respect to perturbation to the input, not to the channel. That's the key idea. So in order to, and so the question is, can a tractor neural network like Hoffman network in some generalized way do this? Well, for instance, Hoffman network can do this, but only up to a linear number of memories, of code words. Hoffman network does exactly this, but only up to a linear, so it would be a terrible code, totally useless for error correcting codes, right? Because error correcting codes have a much higher capacity. However, there is a very puzzling result in modern neural system, which is the following. If you take the Hoffman network is symmetric. So if neuron I and j interact by a weight which is wij, wij is equal to wji. It's symmetric. In this way, you can show that the update dynamics minimizes a Lyapunov function, which is the energy of the Hoffman model. But in general, if you think even to real networks, they're not at all symmetric, real networks. And so the idea is, maybe if you take a non-symmetric network, the minimum, all the configurations that satisfy the, say, the dynamical constraints imposed by this network, because the output has to be equal to the sign of the sum of the inputs, so each neuron is implementing a certain dynamical constraint. Maybe the ground state, sorry, this is a physical term, the configuration that satisfies all this input-output relation for all the neurons, so all the fixed point of the dynamics have these good properties. Okay, this was our challenge. Okay, so, and this is what we did. So we consider a model in which you take n neurons, then they are coupled by some couplings that there's no memory here, no learning, just a random asymmetric network. So the joint probability distribution of P of, well, here is J, but it would be a W, right? It's the same thing. Wij, Wji, or Jij, Jji is equal to the product of probability, so they are totally uncorrelated. In this sense, we say they are asymmetric. And each neuron should be aligned with the input signal, which is just, the neuron, it should be the output, just like in a parity check code, I mean, it's just the same thing. And, but we also add a control feedback, right? Just a local feedback. Okay, it's just which corresponds to the diagonal element in this matrix here. Okay, that's it. And then we can construct a cost function that counts how many of these dynamical constraints are violated. Okay, you see that this quantity in the square bracket is equal to 0 if Si times the sign of that is equal to 1, because 1 minus 1 gives 0. So this counts how many errors you're making. But what this means in terms of the behavior of the system, if you're making errors, it means that the variables are flipping, so you're in a chaotic dynamics. So essentially, when this E is equal to 0, you're in a fixed point of this dynamics. Otherwise, you're in a chaotic behavior.
JD does not depend on I?
No, it's the same for all.
It's the same for all.
Yes, just one parameter for all the system. No, that would be, this is the simplest thing you can think of. Okay, and so what we did is to compute how many fixed points you have in this, for this problem. Okay, I skipped we can show that this is actually an exact computation. We did a lot of computation, but there's a theorem showing that this number of fixed points is exponential and it concentrates, so the first moment the calculation is exact, which is this one, and essentially what you find is this. As you change in the limit of large n, and this is JD, sorry for this JD. As you change the control, the local feedback, the number of solution, this is the log of the 1 over n, the log of the number of solution, increases. So you have, as soon as j diagonal, this feedback is positive, you have an exponential number of fixed points. And when j is 0, you have 0 fixed points. So it's very interesting because this system of connected neurons, asymmetrically, they have no fixed points. The dynamics is always chaotic. As soon as you add some feedback, you start to have an exponential number of fixed points that appear. The question would be, how are these fixed points organized? How they look like? And this is how they look like. Well, I think I'm going. So let me tell you directly what is the final result. The final result is the following, which can be proven by a very long and complicated calculation. But if the diagonal term is between, say, 0 and 0, 1, you have just like these isolated solutions that, and there's no way you can find them. Okay? So there's a region which is in which the fixed point exists, but they are kind of golf course holes, and you don't find them. But then there is a region between this critical value and another critical value, where you have an exponential number of dense regions that communicate. And this was totally unknown. And then if you go beyond this value, the dynamics trivializes because this j dominates the dynamics. Clear that if j is equal to infinity, any configuration is a fixed point. So the key result is that you have this region here where this works as an error correcting code. Okay? And so essentially what you find is this is, so the idea is that here you have only isolated solution, no way to find them, but then there is a region in which it works. And in this region, what you can do is show that while the simple dynamics that I've shown you at the beginning always chaotic, if you use the decoding dynamics, which is kind of like belief propagation, some simple modification, I don't have time to explain that because it takes time, but it's a very simple dynamic, it converges and it corrects error. Okay? So essentially there's this region here in which this system behaves like an error correcting code with respect to perturbation of the input. Okay, so this is where we are today. What we're going to do next is to add some learning on top of this, which could be learning by perturbing the weights of the network, or learning in the input, or learning in the output. There are different ways, but what I just wanted to say that this is a dynamical device that has this capacity, which is a bad error correcting code. I'm not saying it's a good error correcting code, but it is good because it for perturbation of the input, not of the channel. Okay, and this was totally surprising. Because it's kind of annoying the idea that you take neurons, you connect them together, and there's no way of making them agree. They do agree, not only they agree, provided there's some feedback, but also there's this region in which they have some very nice computational capabilities. Okay? This to be published somewhere soon. And I think I'm going to stop here because I'm beyond my time, so if you have any questions, you're welcome. Thank you.
Riccardo.
Thank you. Sorry for it was a bit long. Sorry.
Very nice, interesting. So, do you have any question for Riccardo? No question.
You don't have to.
Well, we can discuss later in the whole of the department. We have the credit. So we'll see you anyway.
Thank you.
Dobbiamo vedere che cazzo facciamo.